into screen. We will be finishing ideal gases today. So ideal gases last class we did not really a derivation, it's an extension here. So there's an equation that you know from ideal gases, PV equals to nRT. So it's like an alternate version exists, which is PV equals to nKT. So how do we get that? It's not that complicated. It's just you need to be aware. This is in terms of moles. This is in terms of number of particles. So how do we get this conversion? So we know that 1 mole is number of particles divided by the Avogadro's constant. So what we do is we take that here and we place it here. And then jeta hoy that R by Na becomes a number. So I mean, assume you know what R is, but R ke bola hoy molar gas constant. Okay. And it's something that you need to know. In fact, it's something that you have to memorize because I don't think piche dai. This is 8.31. Okay, joule per kg. Sorry, Kelvin mole. Anyways, that's the molar gas constant. What's Na? Na is the 6.023 into 10 to the power 23, right? So that's that constant, 6.023 into 10 to the power 23. So once you divide this by this, sorry. So once you divide this R by Na, you get this divided by that. That's another constant. It's called the Boltzmann constant. Okay. So what's the purpose of this equation? PV equals to nKT. It's just an equation that incorporates what into your equation, rather number of particles. Why is that more important? Because physics we deal with number of particles more, not the actual moles, but actual number of particles out there. So anyways, ajke wrap up korbo. Is there any question that you have from this derivation? Yeah. Oh, right, sure. So I'll just quickly go through this again. So force was change in momentum by time, and we found this is the expression for force, right? And for the time, we assume that the particle goes back and forth like that. So the time is going to be from there. So to find pressure, pressure is force by area, right? So this particle collides with this area here, but we take the whole side of the container to be our area. And what was the reason? I told you that when a particle collides with a point on a wall, right? It's usually that wall point that gets the force. But in our scenario, the particles actually not collided. They come very close. What do? They repel the wall. So the entirety of the wall faces the force. So the force is actually spread over the entire wall. So what is the area over which the force is exerted? The wall, right? So what's the area of this entire wall here? Y into Z, right? So pressure equals to force, which is what we got there, divided by area, which is Y into Z. So since this is a denominator, this is also a denominator, right? Both of them will become together. So X, Y, Z. What is X, Y, Z here? X into Y into Z. Isn't that the volume of the container? So from there, we get the volume of the container. Okay. Also, once on its way in, right? And particle to collide for it goes back again. So we assume that whatever velocity it started with, it goes back to the same velocity. So তুমি যদি হচ্ছে এখান থেকে এখানে আসো velocity কমে যায় কেন কমে যাচ্ছে because you're experiencing what from the wall repulsion. So just this one movement can't be taken into account because আমাদের equation ফেলে satisfy হচ্ছে না. Our equation is mv minus mv. তার মানে কি velocity the same. So that is only possible if you start from here, slow down, and then go back the equal distance. That's only when this is v and that's minus v. That's why we have to take twice to that. Right. So mean square. This is the mean velocity, root mean square velocity. I'm just actually need to clarify for you because a term problem. What is this? A symbol. This one. Yeah, it's called root mean square velocity, right? What is this? This one. So this one is called root mean square speed velocity or Boolean current. It's been removed of its direction, right? Root mean square speed. Yes, very good. It's called mean square speed. Why? পারফেক্ট, হ্যাঁ। সো বেসিক্যালি যেটা হচ্ছে, এই প্রসেসে যদি মনে থাকে তোমাদের, আমরা কি করতাম ফার্স্ট, উই স্কোয়ার আওয়ার ভ্যালুজ, উই ফাইন্ড দি অ্যাভারেজ, দেন উই রুট ইট, রাইট? সো আমি এই পুরো প্রসেসটাকে যদি স্কোয়ার করি, তাহলে কি হবে? স্কোয়ার করা হচ্ছে, মিন করা হচ্ছে, রুট করা হচ্ছে, and that root is getting squared again. Doesn't it mean that this function is reversed? Because I square rooted it and then I squared it again. So that means this doesn't make any difference anymore, right? So how much are you left with? Mean square. So this is called mean square speed. Okay. So I know you might be wondering, why are we dealing with this? Because in the exam, they'll literally ask you, what is the mean square speed? And then they'll ask you, what is the root mean square speed? So they're two different quantities. Okay. So this is mean square speed. Why do the particles repel the walls? Right. Just to give you context here, why do the particles repel the walls? So we learned that in subatomic level, right? When you have a particle, the particle has a field around it, an electrostatic field. And the wall also has an electrostatic field, because we're at such a small level, the electrons actually provide the field very easily. So when you have your particle approaching the wall, the electrons of your particle experience repulsion from the wall. So it slows down because of the repulsion, and then the repulsion pushes it back out again. That's why the particles don't literally collide. They basically slow down and go back, which is similar to a collision, which is same here as well. Do you think this remote hits the laptop? No, it does. So all levels we talked about it, or you should. Yeah, exactly. So if you zoom in like till the level of atoms, right, they never collide. Why? Because the electrons of the remote is getting repelled by the electrons of the laptop, and therefore they will never come in touch. Then now you might feel like, then where did the sound come from? Why do I feel it? Right? You're feeling the repulsion, and the sound is basically what's moving away from it, air particles, right? So there's actually no contact. In fact, if I keep it here right now, is the remote in contact with the laptop? No, right? Oh, yeah, it's levitate, literally, and then that force is called contact force. যেটা আমরা হচ্ছে over the years change করে we now call it the reaction force, but it's actually a contact force, and that contact force is in its fundamentals electrostatic force. So all contact forces that you experience, they're all electrostatic forces out there. Okay. Anyways, this is also the same thing. Achha, so we are done with the derivation. So this is the equation eventually. PV equals to 1 by 3 nmc square, or P equals to 1 by 3 rho c square. There are variations out of that. So now we'll come full circle. Our chapter will end here, page 61. So go to page 61. We'll start with what you learned first in grade 9, probably chemistry. It's called the kinetic theory of matter, where if you increase the temperature, what increases for your particles? Kinetic energy, right? Why? That's what we're gonna solve right now. Okay, so let's see how did it all come into place. So this is again another derivation. Unfortunately, this derivation has an issue. It can range between 6 marks and 2 marks. So you need to know which one to write where. In the 6 mark one, you have to show full breakdown, and in the 2 mark, you skip some steps. So I'll show you both of them. So let's start with the equation. So we know that you have P equals to, this is the derivation or the equation we derive, P equals to 1 by 3 rho c square. C is just velocity for the moment, right? Acha. Ekhon, we also saw last class that this density is actually what? Breakdown of density? Mass by volume, right? So capital M by V Legwami. And I'll put a side note here right now. Capital M is mass of one molecule or mass of the entire gas? Entire gas, okay? So this is mass of gas, total mass. Right. Ekhon, I can take the V to the left-hand side, and what will I get? PV equals to nRT, right? So if I take the V to the left-hand side, I will get PV equals to nRT, no, sorry. PV equals to 1 by 3 mc square. Are you with me so far? Achha, what is PV equal to? nRT, right? So nRT equals to 1 by 3 mc square. Now, how can I convert total mass of the gas in terms of number of particles? What is the equation? Yeah, what was it? Yes, exactly. Capital N into small m. Why? This is total number of what? This small m. Yeah, this is number of particles. Number of particles. And what is the small m? Mass of one particle. Okay, this is mass of one particle. Mass of single particle. Do you agree that the total mass is equal to the mass of one particle into total number of particles out there, right? So if I replace that here, I get what here? nRT equals to 1/3 nm c squared. Achha, okay, now we need to do something. Can you tell me what's the relationship between capital N and small n? Inverse. No, actually equation. The relationship between capital N and small n. Capital N is number of particles, small n is number of moles, right? What is the relationship? Achke korlam, acha, just reminder, 5 minutes to hoy nai. Nah, yeah. Yes, this mole number equals to total number of particles divided by the constant. Bishash koro na? Okay, 5 minutes again. So anyways, so I'll replace this with that. Okay, so what I'll have here is n by na times r times t equals to 1/3 nm c square. Can you tell me what cancels out? N cancels out. Also, what's r by na? Yeah, that's the constant k, right? Boltzmann constant. So kt equals to 1/3 mc square. Under mk equation, I want to find link between temperature and kinetic energy. What's the formula for kinetic energy? Half mv square, right? It looks like we're a little off. Under key value 1/3, right? And you can just say this is also k. K is half mv square, right? Is there a way I could make this half? Yes. So what you're going to do is you will multiply both sides by 3/2 and 3/2. Why is that so? Because if I multiply, this is completely legal. You can do this. You can multiply the same numbers on both sides of an equation and it's completely fine. Okay. So you can do 3/2 multiply 3/2 multiply 3. I have not done anything wrong yet. But the 3 and the 3 here cancels out, right? So eventually you get 3/2 kt small k, 3/2 kt equals to half m c square, which by the way is what? K, right? So this is kinetic energy, half m v square. Our 3/2 is a constant, k is also a constant, right? So eventually, what can we say here? That the temperature is directly proportional to the watt of the particles, kinetic energy. And this is what the kinetic theory of matter stated all those years back, grade 9 issue, that temperature barle particular K, right? This is the evidence of it. But it is only possible for something though. What? Gases, right? Because now you'll see that this equation doesn't have what energy involved in this statement here, potential energy. And that's the reason why temperature barle potential energy change. Remember, we kept saying it, but we never gave a proper reasoning. That's the reasoning, okay? Because এটা যদি এরকম হতো plus P, তাহলে you could say, oh, it's a potential barle temperature barle, but you can see clearly that the equation has no potential energy involvement. So entirely, the temperature relates to what of your particle? Kinetic energy, okay? Yeah, bolo. The first one, you increase temperature because you're providing some energy source, that's the K increases, not the other way around. That the K increases and suddenly things get hotter. Same, right? We increase the temperature. No. Yeah, if you provide thermal energy, there's a point where temperature doesn't change, right? But state changes. So at that moment, the temperature is not changing because the so that's another way. You're right, actually. That's the measure of kinetic energy is watt of a material, temperature. So that's how we measure K of material. So if I know this object is cold and I know this is warm, I can say that the K of this is higher than the K of that. But it's not that the K is given the temperature, it's just a measure of it. So if you have a lot of K, you'll have a high temperature. Okay. So this is the most elaborate version you have. Now there's a shortcut version. It's all going to be like 2 marks, 3 marks. Where does the shortcut take place? I think you can probably figure it out. Where do I take the shortcut? How can I make this 2 marks? Which is actually more challenging. So I'm বলি কি করব? P equals to 1/3 rho C square. আবার I break down করব. So PV equals to what? 1/3 MC square. এখানে আমরা directly কি লিখব? NMC square. PV এর জায়গায় আমরা NRTR লিখব না. We'll use that other formula we derived. What was that? PV equals to literally আজকে, okay? 7 minutes ago. What is this? Yeah, okay. So PV equals to NKT. That's the thing. The reason why this became very elaborate, I don't know if you've noticed it, I actually derived the NKT here. So that's why it became a little longer, right? So you can just write here NKT equals to 1/3 MC square. Sorry. Yeah, NMC square. এখন দেখবা যে it's done. So and then cancel out হয়ে যায়. তুমি হচ্ছে 2 দিয়ে multiply করবা. So 3/2 KT is equal to half MC square. This is like the smaller version. Depending on marks, you decide which one you need to write. Okay. The maximum I've seen is 5 marks. So 5 marks it touch left it, and recent papers go data shit. So yeah, these are your derivations. Copy now. I'll give a note on this. What to do with this information. বলো কনফিউশন থাকলে which page? 61. Yeah, 61. Are you guys done? Right, it comes from electrostatic attraction. No. No, exists but it is so negligible because the mass is so small that it account process. Okay, let's move on. So we are done with gas laws. Finally, এখানে হচ্ছে last year PV equals to 1/3 nmc square and PV equals to n kg. To deduce that average translational Ke is 3/2 kg. That's what we just derived. Okay. Also understand that root mean square speed or CRMS is given by that symbol. So that's your gas laws. It's multiple chapters if you remember. It was thermal physics. It was the internal energy. It was that equation U equals to Q plus W, right? It's the problem is that I couldn't do any questions earlier because the questions they provide is usually all combined. There's no just thermal or gas laws. It's generally a combination. So we'll do now a couple of them, okay? So the next chapter is simple harmonic motion. A very interesting topic, very small topic as well. But next class is start করব. Ask you, we're just going to solve questions from this chapter. So first question হচ্ছে yeah, page 63 to go. Page 63. Okay, it says that kinetic theory of gas states of gases leads to an equation half mc squared equals to 3/2 kg. The question is explain the significance of the quantity half mc squared. What is this actually? Yeah, but are to specify what kinetic energy of the particles, right, in a system. Acha, that's not enough. Yes, okay, because আমরা এখানে c নিচ্ছি না, c মানে কিন্তু হচ্ছে we are taking the what velocity of the particles average, okay? So the correct definition হচ্ছে like if exam they ask for it, this is the average translation মানে হচ্ছে movement, okay? Average translational kinetic energy of the they normally provide that in a mark scheme, not mandatory, but I think it's safer because kinetic energy can be of multiple types, right? Do you remember which are the types? Rotation, yeah, rotation, vibration, translation. Okay, so this is the average translational kinetic energy of particles in a gas. Use the equation to suggest what is meant by absolute zero of temperature. So absolute zero is when temperature is zero, right? But what does that mean? Yeah, exactly. Okay, so according to the equation, when t equals to zero, by the way, the t here is always going to be in what scale? Yeah, absolute temperature. There is really no place in your syllabus for degree Celsius, so you can always convert to Kelvin safely. Okay, according to the equation, when t equals to zero, the kinetic energy of the particles Okay, so let's look at these questions. They're gas law questions of your A levels. Actually interesting, not difficult. Just the scenarios are very interesting. Okay, mass change, which you never had like in O levels. Right. So done with the first two. So your question pattern, by the way, in the exam is always like this. They'll give you a couple of definitions, some basic theory, then a math, and sometimes like a conclusion based on the math. Okay, so that's the format all the time. So yeah. In this question, I think there's going to be a math. So let's look at this. It says that two insulated gas cylinders, A and B, are connected by a tube with negligible volume. So you're connecting the two tubes. The volume here is negligible, so you don't need to worry if there's any gas trapped there or not. As shown in figure 3.1, each cylinder has an internal volume provided. So I'll take a picture of this. Right, so each cylinder has an internal volume of 2 into 10 to the minus 2 meter cube. Initially, the tap is closed and the cylinder A contains 1.2 mole of ideal gas at a temperature of 37 degrees Celsius. B contains the same ideal gas at a pressure of that much, temperature of that much. Calculate the amount in mole of the gas in cylinder B. Right, I'll be asking questions here. Can you tell me what equation should I use to find the number of moles in the gas, given that I know temperature, pressure? So question is that you have this container here. This container contains pressure of that much. Its volume is given. Its temperature is given. The question is asking you to find out how many particles are here in moles. So how do you find this? What equation do you use? Okay, suggest an equation. Oh, no, not that one. Can you try it? Yeah, exactly. The ideal gas equation, PV equals to nRT. Okay, so এখানে কি হবে? PV equals to nRT. Our pressure here is going to be 1. করতে পারো, but ওরা moles এ যাচ্ছে তো n তো আসবে number of particles. So pressure is 1.2 into 10 to the power 5 into volume is 2 into 10 to the power minus 2 equals to n into R is 8.31 into what is the temperature here? What should it be? 37. Yeah, 37 plus. Yes, exactly. Okay, taking the careful. 0.15 না দিলে হচ্ছে, I don't know why, but they are very adamant that the 0.15 must be included. So yeah, কত সেটা করলে? And 0.9792. Do we write our answer to 3 significant figures or 2 significant figures, or what do you think is the right? Yeah, 2. So if you look at the data, they're very consistent. All the information is given to 2 significant figures, right? You have to do that. You have to maintain your answer to that same significance, okay? So PV equals nRT. Is it okay? Technically, no, because you're not doing anything wrong, right? It's generally you write to 4 significant figures, then that information is not there anywhere. However, which one would be a better answer, 0.9 or 0.924, let's say? Which one is more appropriate here? Instead of this, let's say you had to write one of them. 924. So the correct answer is actually this. And the reason behind that is none of your information here has how many significant figures? 3. So it'll act at risk, because how did you get so much significance, right? 0.9 lack of problem, because all of them can show to 0.9. So you can always round down, not up. So the tap is open and some gas flows from A to B. So you open the tap and gas from here will actually flow to that side. First of all, each cylinder has an internal volume of that much. Initially, the tap is closed and the cylinder contains that much. So there's gas here. Okay, and there's also gas there. So the tap is open and some gas flows from A to B. Using the fact that the total amount of gas is constant, determine the final pressure of the gas in the cylinders. So the gas is mixed, and you need to find out what's their combined final pressure. So can you try this? That could guess it. I think it's 0.93 actually, the math. 93. আচ্ছা এখানে বলছে each cylinder has internal volume of this much. Initially the tap is closed and cylinder A contains 1.2 mole of gas. So it's a 1.2 mole of gas, and temperature is 37 degrees Celsius, and cylinder B contains the same ideal gas. So the same ideal gas here with the pressure of 1.2 into 10 to the power 5. Do you guys realize why is this a question? Like, they ask this question because look at this. What's the amount of moles in cylinder B? 0.93. What's the amount of moles in cylinder A? 1.2. If I mix them, right? Can you tell me what must equalize for them to mix? Pressure, because pressure is what drives the particles around, right? So the common thing is going to be pressure. So what you need to do here is do your math and figure out when these particles mix, right? What pressure do they attain? That's the question. So that's what what equation do you need to solve this question? PV equals to nRT. I'll just go through the equations one more time. I'm recapping this topic. So if you have missed it previously, key formulas, because some of you are thinking there must be many formulas out there. It's only two formulas. PV equals to nRT. P equals to 1 by 3 rho C square. And this is not really a formula, but tau helpful. 3 by 2 kT equals to half mc square. That's it. These are all the equations you have in ideal gas. Okay, so next time you're trying to solve a question, it's somewhere here. One 1.4 into 10 to the power 5. 1.37. 1.4 into 10 to the power 5. The problem. 1.35. Also 1.35. Do you have an opinion on what should be done here? What will you do? Make P the subject. P equals to nRT by V. And for both of them. No. Then what are you finding? You have removed the thing that you want to find. Equation N. That's a Shabby constant. N is same. Is the volume constant? Yeah. But depends. What are you taking into consideration? This is basically testing your analytical skill. Not physics. It's can you analyze the situation and come up with a solution? So I'll repeat this one more time. You have some gas here. You have some other gas here, and you open the tap here. What happens is the gases mingle, right? So gas from here, gas from there, they mix around. And as the gases mix around, they eventually stabilize at a particular pressure, right? And we know that what must be same for them to stabilize? Pressure, okay? So what is that pressure at which they stabilize? How do you find it? আচ্ছা ওটা করে তোমরা ওটাই করছো আচ্ছা so that's one way I don't know anyone else tried anything else yeah sorry no they will remain the same the temperature doesn't change it's a did they mention somewhere the temperature won't change same yeah it's a fixed temperature but thing is that if the T is the same, it's not a criteria for gases to stop flowing. Gases stop flowing when what's the pressure. আচ্ছা আমি বলি কেমনে করতে হবে you can try this which is take this whole thing as one container you could predict Russian but I'll show you what I'm going to do right now. Look at this process. So you can take this whole thing as one container. So if I take this whole thing as one container, can you tell me what's the total volume going to be? Yeah, so 2 into 10 to the power minus 2 into 2. That's my total volume. What's my total number of moles going to be? The addition of both the moles here. What's my R? That's it. What's my temperature? 37. Wouldn't that give me what's the total pressure of this system as 1? You get my point? So I'm going to take this as one system. And then how do I do that? I take their total volume, total number of particles, total temperature, which all I know, by the way. Okay? যেটা problem এখানে স্টুডেন্টরা কি করে? They try to split up moles, they try to split up pressure, and eventually they make a mistake somewhere. They also split up temperature sometimes, right? ওটা কিছু হচ্ছে না. So what you do is just straightforward. PV equals to nRT for the new scenario. P is unknown. What's the new volume going to be? 2 into 10 to the power minus 2 into 2. And there was a hint in this question that they probably wanted you to do this because they said something. Ki bolche? Yeah, that the gap here, I think, yeah, connected by a tube of negligible volume. Because some students will not want to connect them. They'll feel like, oh, it's wait a second, there's some gas there. Maybe it will hamper. It doesn't hamper. So you can actually take the whole system as just two of these things. This thing doesn't really exist. Okay. So if I do that, what is my number of moles? It's going to be the total mole we have, 0.93 plus 1.2 into R is 8.31 into temperature is going to be 37 plus 273.15. So from here, P would be the answer. Can somebody check the answer? Right, 1.37 into 10 to the power 5. তোমরা যদি তোমাদের ভাবে করে answer পাও, it's completely fine. Okay, I'm just showing my version of it. I think this is more intuitive. বাকিগুলো যদি it makes sense to you, stick to it. There's nothing wrong with that. Yeah. Could we use this one? No. We couldn't use any of them because all of them have volume consideration taken into account. Okay, so that is that one top part. Gas plus yes, this is very important. Page 66. Perfect question. Page 66. Okay, the pressure P of an ideal gas is given by the expression P equals to 1 by 3 nm by v c square. Explain the meaning of the symbol c square. Can you try? What is c square? Just c square. Average speed. Yeah, we don't use average. So does anyone know what's the difference between average and root mean square? They're very different, right? Average is what? You take all the values, just add them up, and you divide by what? The number of values you have, right? That's average, that's mean. Root mean square is a little different. What do? You first square them, then you find average, then you root them, right? So that triangle symbol that you see here is basically that. So the question is, explain the meaning of this symbol here. The bracket like that and the c square. So what would it be? Anyone? Yeah, so that's the reason why I was coming to Parlam, because I find like some students forget that here. Okay, so this one is called root mean square speed, and this symbol is mean square speed. Okay, so whenever you have the C here and there's a square there, we call it the mean square speed. Okay, so yeah, for how many marks? 2 marks. Okay. Yeah, so explain the meaning of this. So this is mean squared speed of the gas particles. Okay, let's move on. Next, the ideal gas has a density of 2.4, pressure of that much, and a temperature of 300 Kelvin. Determine the root mean square speed of the gas at 300 Kelvin. Mean and square. There's some students who just say mean velocity. So they'll get just 1 mark. So there are 2 parts here. And if it was without that square, what would the answer be? If this root mean square, and sometimes they get 3 for it, because the root is also a mark. Because we squared them, right? And once you squared them, you have removed their direction. The plus minus goes away. All right, so can you try? Ashin, what do you do here? What formula do I use to find the mean square speed of root mean square speed of a particle? No. Remove it all. Density. No, the total formula teacher. Oh, pressure equals to into mean square. Right, correct. Okay. So which formula P equals to 1/3 rho C squared. That's it. Just use the equation. You should have your answer. But do I find C square or do I find C here? C, because it says RMS, right? So pressure is 2 into 10 to the power 5 equals to 1/3. Density is 2.4 into C is C squared. So C বের করতে হবে। কত আসে C দেখো? 500. হ্যাঁ, it's a problem. Because just C square মানে কি তুমি একটা পার্টিকেলের ভেলোসিটি বলতেছো। আর বাট আমরা তো একটা পার্টিকেল দিয়ে করি না, আমরা কিনে করি অ্যাভারেজ, রাইট? সো দ্যাট next, calculate the temperature of the gas for the atoms to have an RMS speed that is twice that calculated in I. So at what temperature, right, the particles will have an RMS that is twice the value we found here. So if you can figure this out. So I try, bro. Yeah, it's 3/2 kT equals to half mc square, where your k is Boltzmann constant, which is how much? 1.38 into 10 to the power minus 23. And you may not need that, but anyways. It's a little interesting because temperature barle, velocity barbe. I'm doubling my velocity, so temperature should double, right? The answer is not double. That's just 3 marks. Did you just understand what I said? If temperature and kinetic energy are directly proportional, right? Wouldn't doubling your velocity mean temperature should double? Right. That's why it doesn't work, correct? Yeah, you can just do unitary method. In fact, that's recommended. 700 and can you try something? 1000 divided by root 2. Tell me something. Is temperature directly proportional to speed? No, it's not. Temperature is actually directly proportional to what of speed? Square. That's the only catch. So তোমরা unitary method যদি করতে চাও, সেই two methods, okay? Unitary method কি হবে? Temperature is directly proportional to c square, right? So when my temperature is 300, what's the speed? 500 squared. So when the temperature is unknown, speed আমি কি করতে যাচ্ছি? Double, right? Double মানে হচ্ছে 1000 squared. So yeah, এটা solve করো. So t equals to, wait, did I make a mistake? 1000 square into 300 divided by 500 square. Check what the আসে. I think answer is different. 1200. Right. আমি যেটা বলছি ওটা হবে না. I thought they're doubling temperature. আচ্ছা, so এটা কত হবে? 1200. Do you get 1200? ঠিক আছে, 1200 হবে. Easy idea here is that you're doubling speed, right? So isn't there a square factor? So whatever the other effect is, it's going to get quadrupled, like square of 2. And if you don't understand unitary method, you can do the old way. 3 by 2 K. What's my temperature here? 300 is equal to half M. C is 500 squared. And then find like a constant for M. And then again repeat the value with 3 by 2 K. It's a class session. I'll take 5 minutes extra. 3 by 2 K. This 300 জায়গায় কি আসবে? Unknown temperature equals to half whatever M you found initially, 1000 squared. I don't recommend this because essentially you're just doing something that is just that. You'll probably do this if you don't understand unitary method. Okay. Huh? Yeah. So yeah, this is going to be 1200. The gold one, correct, right? Yes, sir. So yeah, we have just one more question that I'll keep for later on when we recap. Before I end, I want to give you heads up about the next chapter, okay? Because it's important that next class I can start right away. So we're done with gas laws. I'll update whatever is missing here. So our next chapter is called simple harmonic motion. I'll just take 2 minutes to explain what this chapter is all about, okay? So look at this. I'll show you an animation. That should be it. So can you tell me what's an oscillation? What's an oscillation? Yeah, oscillation হচ্ছে something that undergoes cyclic motion. So anything that goes back and forth and comes back to the same place in a certain time. Okay. So can you give me examples of oscillation other than a pendulum or a mass? Swing. Swing is like a large pendulum, but swing is a very good answer. Anything else? Like an example of an oscillating system. Clock, yes, it's an oscillation. Yeah, the satellite undergoing circular motion around the Earth. That's actually a very good oscillation. Random things oscillate. You'll find a leaf on a tree just going back and forth. That's an oscillation as well. They're not systematic. Yeah, the springs that go up and down. Yes, springs, but springs and pendulum chara, for example. So anything else? Yeah, particles in a solid vibrating. That's an oscillation. What was it? eyes. That's not oscillation. That's not natural. Door. Oh yeah. So if you have those yeah, revolving doors বা হচ্ছে হলো ডাইনারি ডোর থাকে এরকম ব্যাক এন্ড ফোর্থ করতে থাকে, রাইট? ওগুলা কিন্তু হচ্ছে অসিলেট করে। But look at this one right now. So I will turn on the system here and you can see here there are two oscillations going on. একটা হচ্ছে a circle. A circle is a very good oscillation. Okay, it's the best oscillation out there. Perfect, same, repetitive, time period constant. That's the best example. On the right hand side, I also have an oscillation. That's an oscillation of a what system? It's called a mass spring system. Okay, mass and springs, they oscillate. Now, what we'll do right now is I will change the direction here of this board. And as I change the direction of the board sideways, you will find that from the side, both the mass spring system and the circle are doing what oscillation? Exactly same, right? Do you see sideways here from the? So the point I'm trying to make here is that even though these are two different systems, right? Do you see that they follow each other around exactly the same way? But if I change the orientation, you see this is going in a circle where that's just going up and down. Now, turns out that spring is actually undergoing circular motion. I know it's difficult to grasp, can we introduce the topic there? That spring is actually undergoing circular motion. Now, you might wonder, it's not though, it's just going up and down, right? Let me define. So, do you agree the object in the left is undergoing circular motion? Yeah, and as the object in the left is undergoing circular motion, if you consider its vertical motion, just going up and down, forget the sideways motion. If you just look at the upward motion and downward motion of that ball that's undergoing circular motion, and if you look at the upward and downward motion of that mass on the spring, aren't they mimicking each other? So if the one on the left is undergoing circular motion, why wouldn't you say the right one is also undergoing circular motion? It is not going in a circle, I understand, but isn't it replicating something going in a circle? So any object that oscillates and its oscillation mimics the motion of an object in a circle is called a simple harmonic motion. There are only two out there in the whole system of, it's a mass spring system and a pendulum. So okay, so a mass spring system will undergo an oscillation that will always mimic a what motion? Circular motion, and a pendulum also does that. So the pendulum going back and forth, if you look at the position of the pendulum bob with a circle going around in a circle, you find that it always follows it around. And these kind of oscillations are called simple harmonic motion. Why are they important? Because their motion equations are all the same equations for what motion? Circular motion. That's why we have this chapter here, because we just did circular motion. Now we're going to incorporate two systems together. Okay. So next class, I'll derive and show you how they are the same. Okay. Because অনেকে লাস্ট উইক দিতে পারেনি, they had some school issues, so আজকে অনেকে দিচ্ছে। আজকে পারবো না। আচ্ছা, মানে well, Thursday was the last date, but I made exception for this week. So what you can do is you can give the test. Maybe you'll get your paper a little later, but you can give the test. So ask na parle Monday to the paper. Yeah. Okay. You know the syllabus, right? It's the thermal physics.